So thanks everyone for joining this session. My name is Dipankar, and today I'm going to talk about Apache XTable and how you can interoperate between different Lakehouse table formats like Hudi, Iceberg, and Delta. A little bit about me. I'm Dipankar. I'm currently a staff developer advocate at OneHouse.ai. I've been currently I focus on open source projects like Apache Hudi, Apache XTable. Previously, I have also contributed to projects like Apache Iceberg, Apache Arrow, and my focus has been pretty much in the data architecture space. So in terms of the agenda, we will start with background on the Lakehouse table formats. If pretty people are aware of it, it will be kind of a refresher in a way. And then we'll go to the second part of it, which is which format to choose and how XTable comes here and brings about the interoperability perspectives here. And finally, we'll talk about the technical overview of it, go into more of a detail presentation around the technical nits and bits. All right. So over the years, organization kind of have been heavily investing on building centralized, reliable, and scalable data platform, right? So the whole idea was if they could democratize data, it would allow more data consumers like data analysts, data scientists, right, to use it, and they can further enable workloads like BI and machine learning. So data warehouse were kind of the first one that enabled to deal with this, but then it lacked kind of abilities to deal with unstructured data for more advanced use cases such as machine learning, right? Uh, and then came the era of the data lakes, right, with the Hadoop ecosystem, which was on premise, and data lakes were kind of great, right? Organization could basically store all of their data, whether it's structured, unstructured, didn't really matter, into a file system like Hadoop file system. And then eventually, with the rise of cloud and its kind of cheap price, we have the cloud data lake storages now like S3, Azure Blob, Google, all the three major vendors, right? So you can basically scale out the storage as you would like, and you have no limitation. I mean, in a way, it's kind of like lesser and cheaper cost. But of course, there were problems, and of course, why we have the lakehouse architecture, and why we're talking about all of this. So one is you can't just dump all of your data into a data lake, right? And have your analysts and scientists to deal with the physically stored data. So what I mean is, if you wanted to do BI, you still needed to organize the data and get it out in a more structured form, right? So you typically use the data warehouse again, kind of a two-tier kind of architecture where you have data lake and data warehouse. So it was kind of costly as well and high maintenance. And the most important problem was that data lake, they lack those atomicity and consistency guarantees, right, with transaction. So things like updates, deletes, you cannot do ACID-based transactions on the data lake. So for example, if two concurrent writers are writing to the same data set at the same time, there are no guarantees that things might succeed or fail, right? And also, it was really getting hard to make sense of all of the data, because in a data lake there is no real governance, no real quality checks, and people usually you dump the data as you collect from operational system. So it's really hard to make a decision and run analytical workloads on that kind of thing when you don't have those quality and governance policies. So these kind of gave rise to a new architecture platform, which is like Data Lakehouse. And as you might have guessed from the name, it's a combination of the data lake and a warehouse in some form. But of course, this is not just a mere combination of the two in a way that kind of it satisfies the needs. But the idea is to basically take the best of the both worlds, right? For instance, data warehouses, they have great data management capabilities, right? And optimization capabilities, things like compaction, clustering, ability to do things like time travel, schema evolution, right? So these are the things that were previously available to users and customers using data warehouses. And similarly with data lakes, they provide the scalability part, right? I talked about even the cost wise, the object stores are very cheap comparatively, minus the egress fees and stuff, which is really great. So a Lakehouse architecture basically builds on this idea, and the most important kind of things that ultimately lays the foundation is kind of the table format in a Lakehouse. So let's kind of talk about the various components at a very high level and quickly. So I'll start from the bottom up in this particular diagram. So if you see in the bottom part, you have the storage, which is the cloud storage. This is where your data lands after ingestion from let's say transactional system, operational system, CRMs, right? So Azure Blob, Amazon S3, Google, all these vendors provide any kind of object store, and it provides the required performance and security on that as well. And then we have the file formats on top of that, which is where the actual data is stored, right? Usually in columnar format, providing advantages like in reading or sharing the data, and also compression-wise, performance-wise, is really good. So file formats like Parquet are commonly used, ORC, even things like JSON, CSV. It can be pretty much anything. Again, the most important part on that layer is basically the transaction database layer that you see on top of the file format and the data lake storage. That's where the table format comes into the picture, right? And that's what basically table format does. So at a high level, what table format does, and we're going to talk a bit more about it in the next slide, but it kind of abstracts the physical data structures complexity, right? And allows different users to like have a schema, kind of a table schema, without having to deal with the kind of physical bits and bytes. Okay, so Apache Hudi, Iceberg, and Delta Lake, they are like the three popular table formats and widely gaining enterprise adoption. But obviously, in the past, we have had the Hive table format from the Hadoop world, which kind of led us to like even today's like format. And on top of the the transaction layer, you see the compute engines and the BI tools, the ML frameworks, whatever is responsible for like interacting with the data and like and kind of like consuming the data. So one question that always came to my mind when I was understanding a Lakehouse architecture is how does it relates to like existing architecture, like a data warehouse, right? So the main distinction between a data warehouse, if I have to compare, and something like a Lakehouse, is that each of these components that you see here in this particular slide are not bundled up into one single system in a data warehouse, like in a data warehouse, right? What I mean is that all these components that I talked about, they're also present in a data warehouse, but the file format and the table format part are kind of proprietary, which is like very much designed to work with their own compute engine. And that's kind of what locks you in a way, right? Because you want to like you have to load the data into their storage, and then you only can access the data from their compute engine. Again, I'm kind of seeing the pattern slightly changing with kind of customers' need. So now even we have warehouse vendors supporting different table formats. But if you're interested to like deep dive more into table formats and the Lakehouse's architecture, I really suggest reading the Lakehouse paper by Databricks. I also published a paper during my time back at Dremio, where we kind of compared it with data warehouse and looked into like how it kind of compares with that kind of angle. So what is a table format? So usually with databases, we have seen the concept of table, right? Yeah, it's not a new concept, right? Companies like Oracle, Microsoft, they have been doing it with relational databases for some time now, right? So like I said, it's basically a way to organize a datasets file to present them as a single table. So users don't really have to know about the physical bytes and files, and they can just have that abstraction on top of that. So in the big data world with Hadoop and HDFS, we ended ultimately with the Hive, format, right? It was kind of important because we wanted more people to like use more data on the data lake. Otherwise, you'll have like data engineering teams writing complex MapReduce algorithms like to process the data, which can be really cumbersome, and it's really limited even skills wise, right, to a particular set of people. So with Hive, we have a table in the database, and it's composed of one or more directories, right? And you have one directory here, but of course, there are a lot of directories in production, and the content of the directories files are the files itself. So the Hive table format was one of the table format that kind of gave us those ACID-based like transaction on top of Hadoop data lakes. But today we have come a bit off from the Hadoop ecosystem, and in a good way. I mean, it's all inspiration, right? So. And now we have three major table formats, like Hudi started from Uber camp, like Iceberg started from Netflix camp, and Delta came out of Databricks. Overall, the goals of these formats are kind of same. And some of you may already be aware of these formats, but folks who are new to the space, just a bird's eye view of what these formats look like and how they differ, right? So like I said, these are basically the metadata layer on top of the actual data file, the Parquet files, for example, right? And how these metadata files are organized and designed are a bit different, and that's the only difference you see. For example, Delta, does this with this JSON-based, transaction log. Iceberg uses a bunch of metadata files, and Hudi kind of takes a timeline-based approach and indexing. So once you have the kind of metadata abstraction on the files on storage, you can now explore fundamental characteristics like SQL semantics. You can write SQL queries on top of that, and do things like schema evolution, for example, time travel, right? All those data warehouse capabilities are now capable here. And also this metadata files allows you to track like statistical information about the data files, which are super important for like things like performance optimization, performance tuning. Those are really the benefits of this. So like I said, although these three table formats came out of three different camps, the goals are obviously mostly the same. The goal is that customers should be able to like have a open data architecture, meaning the data should not be like locked into a particular system where they can only bring in one compute engine. So that's the whole idea behind it. Now, coming to the main point, the thing is fundamentally these three table formats are not much different, like I said, right? When data is written to a kind of a distributed file system, these formats have similar structure. And it's kind of like an abstraction on top of the Parquet files, right? For example, if you see the Hudi table format structure, right? You see the .hudi metadata file, and you see the bunch of Parquet file. Similarly, for the Delta, you see the transaction log, and you also see the per K file, right? And for the Iceberg, you see the manifest file, the metadata file, the manifest list, along with the per K file. So the intersection part, the common part here is the file are pretty much the same. The metadata is the only thing that is changing here. So that brings us to the $1,000,000 question, right? What format should you choose, right? This is probably one of the most common questions I have received in my 2-3 years of working with like customers in lakehouses and productionizing lakehouses. And to be honest, this is a tough question, right? Everyone's workload, use cases, ecosystem, they are different, right? And so there are different factors to consider in this case. You'll probably see a bunch of like comparison articles around the same, that kind of targets things like performance, features, community. But it's a really difficult thing to compare and choose and really stick to one format, maybe. But to give you a feel, here are some guiding principles, right? For example, like Hudi can be good for like low latency streaming based pipelines, for example, right? Delta could be good if you're already in a database environment and it's kind of easy to get started as well. Whereas Iceberg, it works with like Dremio, it's pretty much like the compatibility wise, people are building it. Even things like partition evolution is very unique to like Iceberg, hidden partitioning. So these are some of the things that are really like where Iceberg shines. So overall, it's kind of tricky to nail down and like stick to a particular format and like get married to a particular format, right? So up until now, we have learned that the decision to choose a format can be challenging and involve many costs, right? So the challenge basically lies in selecting the best format, right? And which can be a really arduous task. And the ideal choice may also shift over time as the workloads evolve in your environment, right? And also it's also important to acknowledge the fact that now we are seeing more and more open table formats being developed. Like for example, Apache Pymon is one example, which is kind of like with Fling environment that came up recently, right? And we are also seeing like more specialized table formats, like Havasu, for example, is based on Iceberg, but more for spatial kind of geospatial workloads, right? So ultimately, these are all good developments, right? These are like helping customers like own the data, have open data architectures, and not limited to a particular workload, right? But in general, in the past couple of years, in my experience as well, what it comes down to is it's feature level comparison. Okay, what people do is, okay, maybe Iceberg has this feature, but Delta doesn't have this feature, so that kind of comparison, and it depends on your workload as well. The second part is the complexity of implementation itself, right? How easy is it to migrate or to an existing format or from scratch, right? Are there any additional system dependencies that you need to worry about? And the third part is what type of like community support is that? Is it really open? How open is it? How are the developments happening, right? Because these are all open source projects. And on top of that, there are also some new challenges as we are kind of learning from productionizing lakehouses, right? For example, newer workloads in Lakehouse architecture, they involve multiple teams using multiple different table formats, right? So organizations, they want to go beyond these table formats and be able to like kind of interoperate and like talk with different teams and use the data from different teams. So I think that the challenge is here that you need to be able to interoperate and make your like data. When we talk about data silos, this is kind of in a lakehouse environment. This is what we are talking about in a way. Okay, so the question is, do we really have to choose, or is there any another way, right? And then that's where kind of Apache XTable comes. We have seen this kind of problem, and the solution is basically the XTable that we kind of presenting here. So Apache XTable is not a new table format. It's just a translation layer on top of like the existing table format, right? So the idea is that your data should be universal. The flexibility should be there for teams to choose and cater to different use cases. You should be able to write in one format and use query engine, whatever works best for you, whether it's Dremio for Iceberg, whether it's Spark for Delta, or whatever it is. And the overall idea, I guess, is to write once and query everywhere. So XTable is an open source project that kind of allows omni-directional interoperability. And the reason I talk about omni-directional is because you are not limited to kind of one-off conversion from like one particular format to another. This is more about like interoperating between formats, right? And so that the important part is that it's not a new format. Like I said, it's just an abstraction and set of tools that allows you to translate the metadata, only the metadata part. So the most important part to note here is that we are not touching any data files as part of this translation, right? There is no costly data rewrites. There is nothing happening in the background. The only thing we are doing here is, for example, let's say if we have like an Iceberg metadata, we're going to translate using that metadata and like, let's say into a different table format. That's the only thing we are doing. So the overall goal with XTable is that you start with any table format of your choice. And if there is a specific requirement, right, in your organization, you can switch to another depending on these factors that I kind of discussed, right? And all you have to do in this case, like I said, in this particular screenshot, you can see you can just choose your source table format, choose your target table formats, run XTable, and that's all. You have the metadata there, and now you are ready to like plug in. For example, you can see spark.read.format Hudi. You can read Hudi tables. You can read Delta table, Iceberg table, whatever it is. So again, I'm going to like present a more of a like a kind of a like a high level like a demo, if you may, like to just showcase what we did even with Dremio, like in this case. I'm going to more of a technical level now, like, and understand, like, try to like explain like what basically the XTable's architecture looks like. So at a high level, this is what like XTable's architecture look like. It is comprised of three key components: the source reader, the target writer, and the central core logic itself. So let's kind of take a look at these three individual components. So the first is like the source reader, and these are like table format specific module. They're responsible for reading metadata from source table, and they operate using a pluggable file system, right? So for example, like when I say pluggable file system, today, if you have any new formats coming in, you can just take that interface and implement that interface. So you're not like, writing a bunch of new code itself from a more technical level. It's really easy to like plug into XTable as a new table format as well. And what basically what this particular piece of the architecture takes care is basically it extracts the information like schema transactions, partitioning info, and it translates into XTable's unified kind of internal representation. The next part is the target writer, and this kind of mirrors the source reader. Their role is to basically take that internal representation that we did of the metadata and kind of accurately map it to the target format's metadata structure. And this includes like recreating schema, transaction log, partition details, all this thing in the new format. This is what we're taking care of. And the most important part of this XTable architecture is the central processing unit is basically the core logic. And this particular core logic, it kind of orchestrates the entire translation process, including initialization of all the components, managing the source and targets, handling tasks like caching for efficiency, state management, for example, incrementally processing, telemetry. All these things are being taken by the core, like logical part of this XTable. Okay, so now that we have a decent understanding of XTable, let's understand a bit more like technically what happens during the sync, and then try to understand about the two kind of translation modes or sync modes available. So I use the sync and translation very like interoperably because it's kind of like same thing it means. So XTable provides two synchronization modes. One is the incremental and another is the full. The reason why we have this kind of two mode is because incremental mode is pretty much lightweight and has better performance, especially on large table. So what XTable does, XTable is detects which particular source table formats commit have not yet been translated yet to the target, right? And it kind of focuses solely on converting those commits, right? So this particular approach, by incrementally kind of like reading commits, you are reducing the time and the computational resources, right? And also this allows for kind of, you can like frequently invoke like, XTable on a commit by commit basis, like, efficiently kind of reducing the stateless on your data, right? And if there is anything that prevents incremental mode from working properly, the tool will kind of fall back to the full sync mode, and you go back to like the similar way. So what exactly happens during the sync process, right? So the syncing of data files is very important, right? Along with their like column level statistics, right? Partition metadata. So these are the things that we kind of sync in this entire translation format between the table source and the target. Then the schema updates, right? The schema updates need to be reflected from the source to the target table formats. That's something super important as well. And the third part is the metadata maintenance for the target formats. Like for Hudi, like, unreferenced file will be marked as cleaned. For Iceberg, the snapshot will be expired after a configured amount of time. And for Delta, the transaction log will be retained for a particular configured, amount of time. And, it kind of clears that up later. So just to sum it up, like the high level kind of attributes what XTable provides, XTable is omni-directional, meaning you can start from any format and you can convert to any other format, and you can round robin or round trip, like, you can make any combination that you want with absolutely little performance overhead, because no data ever is copied or rewritten, like I said, right? It's just only a small amount of metadata that we are kind of like, converting, right? The second part is we have two, synchronization mode. We talked about it. The incremental mode is lightweight, better performance, and then the full sync mode is like for the entire like table sync. And of course, XTable is designed to easily adapt and expand, right, in response to like emerging table formats, like I talked about. And this just only means you have to like just pretty much implement like kind of the plugging system, the pluggable file system, and it kind of like opens up avenues for all this translation. So XTable kind of provides a new direction right here to like kind of deal with the tough decision of selecting and sticking with the table formats. Now, while we started with the need for interoperability in this particular talk, it also brings back some critical question, like such as this one from the community. If you read this particular tweet, so the tweet says, taking a step back to view table formats, how many teams out there are running or needing data to be in all formats like Iceberg, Hudi, or Delta? Maybe I'm not seeing the full picture here. I would think one of the format would suffice in an organization end to end. And that's a valid question, right? It's kind of a new way of doing like architecture development, so it's kind of like uh, tough to understand like why we need kind of these different things. So to provide some context, some of the aspects that we want to consider here is that number one, we have compute vendor table format, right? Compute vendor, most of the compute vendor engine vendors today, they are inclined towards a particular format, and they're all for the better reason, right? You want to be able to do better optimization, better feature extensibility with particular format. And doing it for one format is itself is challenging here because we are dealing with so many new things. But doing it for all three doesn't really make sense in a way, right? But this kind of contradicts the initial idea of not locking in data to a specific format, right? And in fact, this is one of the biggest motivations behind an open lakehouse architecture, that you should be able to like interoperate between different kind of like data. The second part is the coexistence of table format, right? Most organizations, and I'm kind of working on like with those customers as well as I'm learning more, they have more than one table format in this architecture, specifically like larger organization, right? Because they want to use these different compute engine which are like developed specifically for that particular format. Okay. And the third part is the rollback or migration itself. So decision to select a table format is correlated with another question, which is what if there is a need to revert or migrate, right? So migration is usually kind of a standard answer. But in this case, it is very like costly and it can involve like tremendous engineering effort and planning. It's really like a lot of input. Okay. So I just wanted to like, I'm not going to do a demo in the brevity of time, but this is what we kind of recently did, and I have a blog and I can share it later as well. Basically, the idea is that Dremio doesn't support Hudi tables today. It's mostly like Iceberg and like a Delta in a way. Uh, but we wanted to like show, okay, what if like Dremio has a like Hudi table and how you can use it, right? So the use case was like, let's say a team A in a particular organization, they are using Hudi with Spark to write like some kind of streaming these workloads, and they're writing data into Hudi, right? And then there's another team B in an organization who uses Dremio with Iceberg, but they also want to use the data set from like the Hudi one, right? And they want to use it and merge it in Dremio and like do their analytics in Tableau or whatever BI tools. So what do they do in this case? So in this case, what we did is we used XTable to translate the metadata. It's a simple translation. So the Hudi table will be exposed as like an Iceberg table to Dremio, and that way Dremio just reads it as an Iceberg table, and you can do your analytics on all of that. Okay, so that's pretty much it in terms of like the what I had into the technical contents. It's an open source project. XTable we just launched with one house, Microsoft and Google in last year, and we are under Apache license 2 in GitHub. So if you want to get involved in any form, feel free to like start a PR or go to discussions. It's also exciting to see some early momentum in the project. These are again very vanity metrics, but it is very important to understand the overall growth of projects. We had like more than close to 700 stars. 1,000 GitHub clones. We were also trending in the GitHub repo worldwide, so that's really interesting to see the kind of trend. Where we are going, our goal is obviously like the seamless interoperability, like I talked about, and eliminate more data silos. And of course, we want to be vendor neutral, so we kind of like donated this project to Apache Software Foundation, and now we are incubated as the Apache project. So that means our next goal is to take it forward as a Apache top level project, so we can graduate it in a way. And I also wanted to like pull up and give a shout out to some of the initial committers involved in this project from various angles and organizations. Like, we have folks from my organization, One House, like Microsoft, Google, Dremio, Cloudera, Walmart. So, really good momentum there, good collaboration and diversify as well. And I'm going to skip this. How to get started? You can just check out our XTable, the documentation site, and it should be pretty easy to like get started. We even have some hands-on example. You can just like use the Docker repo, and you can like open up a container and run your conversion. And that's pretty much it.